So first of all, once again, let's recall what we have learned in the previous lecture last week. We start from the electromagnetic spectrum. I hope you still remember. We know that the wavelength of the electron radiation is related to the frequency and also energy. So we follow this Planck-Einstein relations, which is E equal to energy equal to Planck constant times speed of light divided by the wavelength of the electron radiation. So this equation, I want you to remember. I hope you remember this. And if you use the unit of the energy in electron volts and the wavelength of the radiation is nanometer, and we can we can simplify this equation to become like this: energy equal to 1240 divided by lambda. This is the equation I want you to remember. According to this equation, we understand the visible light, the wavelength of the visible light is in the range of what? It's in the range of 400 nanometer to 700 nanometer. Okay? And its corresponding energy is 3.1 electron volt, which is blue light, to the 1.8 electron volt, which is red light, red color. Okay, so this is a very simple numbers. So I want you to remember this. That will be easier for you to do some simple calculation, or this is become a common sense. Okay, visible light, 400 nanometer to 700 nanometer. Energy from 1.8 electron volt to 3.1 electron volt. Okay, so this is very important. Please remember this. And last week we talked about the Ribel equation, and this is also is the equation I want you to remember, because Bohr atomic model is related to this also. So we know that if n final equal to 2, that will be Balmer series, right? If n equal to 1, that will be Riemann series. If f equal to 3, that will be Paschen series, etc., etc. So you know that the frequency is related to what? The numbers, okay, which is quantized. And this is the quantum number the principal quantum number we are going to talk today. Right, so this is the second key point we learned from last week. And then we know that is it possible to verify whether the atom which has multi electrons still the energy of the electron still quantized, and this is the experiment. Also, we also use the gas discharge tube, right? Okay. So last week we also talked about limitation of the Bohr atomic model. There are three. The first one is called Michelson-Morley experiment. Michelson-Morley experiment tells us that in the spectrum of the hydrogen, in the red color, and there are two lines. The two lines means that the two wavelengths. Two wavelengths means there are two energies, transition energy. So it's either the energy transition of electron is either from N, there are two lines in the N3 to the N2, or two energy states in the N2 from the N3. Okay, so this is the possibility. We think is this double line cannot explain by Bohr atomic model. And then the second one is Zeeman effect. Zeeman effect tells us if you put a gas discharge tube, if you put a magnetic field surrounding the gas discharge tube, the spectrum will split. If you apply electron field, to the spectrum will split. The light will split. This is the first one. And also, if you put the electrical field surrounding the gas discharge tube, again, the line, the spectrum will split. So these three limitations of the Bohr atomic model is interesting, and then we cannot explain these three phenomena by Bohr atomic model. Right? That's why today we are going to talk about the next model, which is the shell model. The shell model is also called Bohr-Sommerfeld model. So again, let's go back to the story of the Michelson-Morley experiment. The Michelson-Morley experiment is that we found out N3 to the N2, the energy transition from N3 to N2 is doublet. So that means it's very, very close. These two lines are very, very close. So again, I just told you that they might have two energy states in N3 orbital, or two energy states in the N2 orbital. So in 1916, Sommerfeld think that, well, instead of orbit which is spherical, because there are some fine structures or some very close energy states. So he thinks that in this orbital they might have some small one. So he thinks that the electron might be described as a elliptical, not spherical. Elliptical orbital means that it's not perfectly spherical. So there's some kind of structure which is not. So if you think of this, and then if you draw this many elliptical orbitals, in the end, you will have a kind of, you become like this. It becomes like a spherical orbit, but there are some elliptical orbitals in this energy state, which is very fine structure inside this. Remember? Okay. If you draw thousands of elliptical orbitals, okay. So this orbit is called principal quantum number N. Okay, I hope you still remember this Bohr atomic model is N. Now they name it principal quantum number. So it's like eggshell with this is an eggshell with thickness, and it looks like a spherical, but in fact inside there are many small orbitals. So for this small orbital, with the N there is a little bit of the fine structure. This is called fine structure, which is Sommerfeld think that there's some fine structures inside this spherical orbits. Sorry. So the shell contains multiple orbits. Okay, this is termed orbitals, or we call subshell. So orbit contain many orbitals. You can call it subshell. And this is the quantum number L. We call this quantum number L. So shell is principal quantum number N, and orbital is new quantum number L. So now you learn there are two quantum numbers. How about Zeeman effect? Zeeman effect is the third quantum number, which we call M. So you have the principal quantum number, which is you can assume is a kind of spherical, right? So for example, this object which is x can be 1, 2, 3, 4. That means the principal quantum number 1, principal quantum number 2, 3, 4. And for L, we call orbit. This is orbit. This is orbital. which is fine structure inside this orbit. So if we use the energy diagram to describe this, which is L equal to 0, and now we know this is S orbital. Okay, and L equal to 1, which is P orbital. L equal to 2, which is D orbital. And this is energy level diagram, which is this is low energy, high energy, and higher energy, and the highest energy. Okay, and the principal quantum numbers, the third principal quantum number M, is that if we apply the magnetic field to this gas discharge tube, the energy is split, right? Or you can apply magnetic field, or you can apply electrical field. Okay, and then if you apply this to L equal to 0, it stays there. There's no splitting. If you apply magnetic field to the orbital, which is L equal to 1, which is PF orbital, the energy will split from 1 to 3 energy states. If you apply magnetic field to the L equal to 2, which is D orbital, then energy will split into 5. 2, 1, 0, -1, -2. Which is what's going on for the quantum number M. So let me give you an example. The energy level diagram of Mercury from 7p to 6d transition. So electron, the energy transition of the electron from the 7p to 6d. And if there's no applied magnetic field, you can regard it 7p L1 P is L equal to 1, D is L equal to 2, right? Okay, so the transition is quite easy from the 7p to D1. And you know this is nanometer. What does that mean? Why this is nanometer? 546.1 nanometer. What does that mean? It's the energy, right? You can use Planck-Einstein equation to convert nanometer to convert the wavelength to the energy, right? Okay, right. So once you apply 1.5 K Gausses, that means you apply magnetic field to this energy, then it will split. Energy will split to 3 levels. For the P, that will go to 3 levels. For the L, for the D, that will go to the that will become 5 levels. So you have many different energy transition of the electron. Okay. Right. So now we learn 3 quantum numbers. The first quantum number is N. The description is we call principal quantum number or shell, or you can call it orbit. Okay. So this is related to the size. N equal to 1 is smaller. N equal to 2 bigger. N equal to 3 even bigger. And because of different studies or different research, the field of the studies, they have different notation. You can have notation 1, 2, 3, 4, like Bohr constant, Bohr atomic model. N equal to 1, N equal to 2, N equal to 3, N equal to 4 to the infinite. Or another notation is called K shell, L shell, M shell, N shell. So you can say N equal to 1 is the first shell, second shell, third shell. But now we used to use K shell, L shell, and M shell, N shell. So example is that, as you know, the N is larger and then the size is bigger. So N bigger than M, bigger than L, bigger than K shell. The second quantum number is L. We call it orbitals, or we call subshell. So there's is kind of fine particle, which is the shape. You know, the shape N equal to size, right? L is a shape like spherical or elliptical, right? Remember? So the notation again can be 0, 1, 2, 3, and n minus 1. What does that mean? This means that if n equal to 1, then L, if n equal to 1, you put n in this case L shell, that means what? That means L equal to 0. If n equal to 2, you put it here, that means there are two stages. That means L equal to 0 or 1, right? That's the first notation, notation 1. Notation 2 is that you call this S orbital, P orbital, D orbital, F orbital. So now, I'm sure, I don't know whether you learned this in your high school or not, but this is or the first year in the in a physical physical classes. So, because this is related to the shape, right? So if L equal to 0, the shape is spherical orbit. If L equal to 1, that's elliptical orbit. If L equal to 2, that will be more complicated, more complex. So by calculation, you will be you will know what's the shape. I will show you a website related to this the shape of the orbitals. How about M? M is we call magnetic field, right? So it's a spectral orientation. So it's a number, or also we can call this is a number of the energy states, because number of the energy state are all get together in one place. But if you apply the magnetic field or electrical field, then you will find out how many energy states in this orbit. Okay, so that will be L minus 1 to the 1, 0 minus 1, and then to the L at 1 minus L and the minus L. What does this mean? Here's an example. If n equal to 1, right? If n equal to 1, that means L will be equal to 0. If L equal to 0, that means there's only one state. That means that M will become 0 in the center. Excuse me. Okay, what does that mean? M equal to 0. M equal to 0 means that no line splitting in the magnetic field or the ground state. In the previous page, I did tell you this, right? Okay. How about if n equal to 2, what happens? If n equal to 2, that means L will be equal to 0 or 1. 0 or 1. And if L equal to 0, M will be equal to 0. And then if L equal to 1, what does that mean? Equal to 1, then M will be 1, 0, minus 1. So there are three energy states. There are three energy states. How about M equal to 2? That will be 2, 1, 0, minus 1, minus 2, right? There are 5 energy states. Okay? Right, so this is what you have learned in first year, I think, the physics courses. And then the first quantum number is called spin. Spin is clockwise or anti-clockwise. You know, the electron will spin either clockwise or anti-clockwise. Right, so now let's talk about the first quantum number, spin. I want to use a very simple way to let you understand. It's more complicated in this topic, but I don't want to go to the details. So this the easier way to let you understand is Sturm-Gerlach experiment. Sturm-Gerlach experiment is that in 1922, they have a metal which is a silver vapor, which is a silver atom, and goes through this divergent magnetic field. So the silver atom, the silver is vaporized. So if you have a solid silver and you heat this up, you heat the silver vapor, heat the silver up metal up to a certain temperature, the silver will vaporize, become silver atom in the space. And then you introduce the silver out to this chamber, and they pass through a divergent magnetic field. This is called divergent magnetic field. And interesting thing is that if you don't apply magnetic field in this path, the silver beam will go to this target with one line only. So the silver atom will hit the substrate like this. However, if you apply the magnetic field to this path, the silver beam will split into two. You can see there are two lines here, and which make you feel what's going on. What's going on? Remember, this is an atom. It's not electron. When we have electron, that means that's the third principal number. The third quantum number. And this fourth quantum number is called spin, which is related to the electron spin. But we use the atom for the experiment. Okay, and then, so with this experiment, somebody need to explain what's going on. So this is the proposal from the Ulebeck and Groundsmith. They propose something like this. They think that there's an angular momentum as a mean of explaining these results. This intrinsic properties has a later term spin by Pauli. Pauli, we are going to introduce this. You know why? Because for the silver, you have only one electron in the s orbital, and there's only one. So if you don't apply magnetic field, there's no effect for these electrons. But if you apply magnetic field, this electron can be spin clockwise or spin anti-clockwise. So that's why they think that a net non-pair spin, this is a net non-pair spin, phi s1 in the silver. Okay, the half of the silver are spin up, and half of the silver are spin down. So we call this clockwise or anti-clockwise. So this is the fourth quantum number. So far you just remember something like this. There are four quantum numbers. Okay, the fourth quantum number is the spin of the electron. There are only two ways, spin up or spin down, or you can call it clockwise or anti-clockwise. Okay, so this is how we explain. Okay, clockwise, anti-clockwise, spin up, spin down. So Sommerfeld saying that, well, let's build another new model I shouldn't say against, to improve a Bohr atomic model, which is we call shell model. The shell model is that the circular structure with the elliptical structure. So we create a new quantum number, Sommerfeld. So in 1916, the electron is related to the three quantum numbers, which is principal quantum number, L, and M. And by the study of the Germlech and Ulenbeck and Groundsmith in the 1925, the quantum number, the development of the quantum number the number of the quantum number becomes 4. So we call this quantum number. The quantum number is the fingerprint of the electron. So every electron in the atom is characterized by 4 parameters called quantum number. So electron, the fingerprint of the electron is quantum number. There are 4 quantum numbers. They are all different for each electron. Okay. Does anybody want to tell me the the fingerprint of element is what? What is the fingerprint of the element? Now that's the fingerprint of an electron, right? Okay, so what's the fingerprint of an element? How can you identify this is carbon, this is nitrogen, this is silver? Yes, please. What? Spectrum, right? Thank you. Spectrum. So spectrum can identify if you got a spectrum, you can realize or you can identify what kind of gas or what kind of element in the gas discharge tube. Thank you. So if you want to identify electrons, quantum number is the fingerprint for the electron. Okay, he's a great man, Sommerfeld. Okay, he's an atomic and quantum physics. He got nominated a record of 81 Nobel Prize in physics, and he never got Nobel Prize. So, is it amazing? He was nominated 81 times, and he never got Nobel Prize. Okay, and do you know they just released the Nobel Prize winner in physics last night? Do you know who are the three won the Nobel Prize in physics? No, you don't, right? Okay, it's related to the electron. Okay, they can detect the electron. They can monitor the electrons by laser, which is a very good, very nice study. Anyway, so but although he didn't get Nobel Prize, but he has many students got Nobel Prize. Okay, so there are many students got Nobel Prize and supervised by him. So in his birthday, 80 years old birthday, all the students come together and they show these two pictures in his birthday. You know, this because he is the one create quantum number, the second quantum number, which is L, right? So if this is circle or spherical, this is L equal to 0, right? If we make it longer, this is elliptical, so this is L equal to 1. Nice, right? Okay. Right. Okay. So now let's take a look of the quantum numbers in a little bit detail here. So the quantum number is the using wave mechanics. Every electrons in this atom is characterized by 4 parameters called quantum number. And we all know that this is N, L, M, S. Okay, some scientists they use M, L, M, S. I will just explain to you the principal quantum number K shell, L shell, M shell, N shell. And the second quantum number, which is subshell, right? So SPDF, the shape of the electron subshells. Okay, and the M is the energy, number of the energy state. The S is the spin, orientations either up or down, spin up or spin down, right? Clockwise or anti-clockwise. So this will be easier for you to understand the quantum numbers trend tracks. So if you have a principal quantum number, the second quantum number, which is L, angular momentum, and third one is magnetic. Okay, and you have spin up, spin down. So this is the trend tracks. Okay, if you have principal number 1 here, and you got from 0 to n minus 1, right? So you have 1, 0 here. And then if you go to magnetic field, you have numbers of energy state, which is 0, right? This is 0. Or if in the track number 2, which is principal quantum number 2, K shell, M shell, right? L shell. Okay, so this is 2. You have 2, 0, and 1, and 0 go to the train track go to 0, and 1 go to -1, 0, and +1. Okay, so you have spin. This spin, you have 2 electrons here, which spin up, spin down. You have 2 electrons here, right? And here you have 6 electrons. Okay, and you have 2, 6, and 10 electrons. Okay. Right. This is the tables from your textbook. So I don't want to waste your time. So just let you have. Let's just go through this quickly. So n equal to 1, 2, 3, 4, which k shell, l shell, n shell, n m shell, n shell, and the l is 0, 1, 2, 3, and n -1. So S shell, P shell, D shell, F shell, and M is like this. Okay, so if the shell k n equal to 1 number will be k shell, and L will be 0. We call S. No? And how do you combine these two together? We normally will use this 1S. And number of the energy state, you will split the energy, that will be 1, right? And number of orbital in shell is 1, and you have 2 electrons. And the shell number 2, which we call this L shell. So this, you have 2 states, 0 and 1, and 2s, and 0, 1, and this is 2p, right? 2p. And you have -1, 0, 1, and here will be 3. So total you have 4 energy states. So you have 4 energy states, and you have 8 electrons. Because one energy state has 2 electrons, spin out, spin down. Number 3, okay, it's like this. So please read this by yourself. So in the number 3, you have 18 electrons. Okay, in the N shell, like this, you have 32 electrons. This is not difficult at all. So I will just go through this. So the electronic structure is that electron has wave-like and particulate properties. So far, we are all talking about particulate properties. We haven't talked about wave-like properties. Because according to the Bohr atomic model, and because according to the Sommerfeld model, we all regard electron as a particle, not wave. This means that electrons are in the orbitals and defined by the probability. We are going to talk about this today, later. So each orbital is at discrete energy level determined by quantum numbers. Okay, just here for your information. Okay, before we talk about quantum mechanics, we need to know the electron configurations. So far, we know that we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, etc., etc. We know these are the energy states. So how are we going to arrange electrons in these electron states? In these energy states. So energy state is like this. For example, if we have n equal to 1, principal quantum number n equal to 1, 2, 3, 4, 5, 6. And then this is energy level. It's small and high, it becomes 0, right? If electron is here, that we call free electron. Hope you still remember. And if electron close to this part is tighten bindings, so energy is high. So you need to difficult to remove electrons away from the atoms, right? So 1s is the energy is very, very low, and 2s, 2p, 3s, 3p, 4d, 3d. And then you might wonder why 4s is here. The energy of the 4s is lower than 3d. This is for some reasons. Okay, it's not 4s is not here. 4s, 4p, 4d, 4f. No, the energy state is here. So the energy of 4s is lower than 3d. The same situation you can find is that 5s is not high. The energy of 5s is not higher than 4f. It's somewhere here. You might say, well, Professor, why 5s is not here? Well, this is, we have some rules to follow. So I'm going to tell you the rules. So what is the fielding sequences of electrons in orbitals? So if I have an electron here, if I have an electron, I can field in 1s, right? Or I can field in a 4p. Or should I field electrons from 1s, 2s, 3s, 3 and 4? Or should I field electrons from 1s, 2s, and 3s, 3p, and then 4s before 3d? What kind of rules we need to follow? And we call this alpha principles. Alpha principles. There are 4 rules for you to follow, and this we put these 4 rules together. We call this alpha principles. Okay, so these are the alpha principles. The first one is that electrons should fill in sequences and energies. You fill electrons to a small energy first. For example, if you have an electron here, and you have to fill 4s first. After that is 3d and then 4p. Not 4d, go to 3s because energy of 5s is lower than the 4d. Okay, this is called electron fielding sequences and energy. The second one is Pauli exclusion principles. One energy state need to have 2 electrons. So Pauli say that you cannot put 2 identical electrons in the same place. No, because you have 4 quantum numbers. All the electrons has his own quantum number, which is fingerprint. So if you put 2 electrons in this energy state, these 2 electrons must be different. And this is what we call spin, right? Spin up or spin down. Okay, this is the Pauli exclusion principle. The third one is called Hund's rule. Hund's rule tells us that I'm going to tell you later. Hund's rule tells us that if you have 3 energy states, before you split it into 3 energy states from high to low, if there's no magnetic field to apply, how are you going to field electrons in these 3 energy states? This is called Hund's rule. The fourth one is NL rules. It's going to tell you why 4s energy is lower than 3d. Why? And we follow NL rules. Okay, let's talk about Pauli exclusion principle first. This is Pauli. He's also a Nobel Prize winner in 1945. So Pauli thinks that Pauli, he is the student of the Sommerfeld. He got Nobel Prize, but Sommerfeld doesn't get Nobel Prize. Okay, and again, he worked as a postdoc with Bohr and Neil Bohr, and Max Born. Okay, he thinks that each electron has a distinct set of the quantum number. So he invented the 4th quantum number, right? So this is S. So he thinks that no 2 identical fermions. The fermions is after that we call the S. Okay, the particles with half integer spin may occupy the same quantum states simultaneously. If N, L, and M are the same, S must be different, such that the electrons has opposite spin. So if these 3 are the same, then S must be different, which is spin up or spin down. Okay, so let's think of Pauli exclusion principle in this stage. So the energy state values of the energy that permitted for electrons. So Pauli exclusion principle is like this: that each electron state can be hold no more than 2 electrons, which is opposite spin. So if I have 2 electrons here, the has to be opposite spin. One is spin up, one must be spin down. Okay, so when you do the job here, you have one spin up, you have one spin down for 2 electrons. Okay, each state have 2 electrons. Then you will have 6 electrons here. And in this state, in the first one, you have spin up and spin down, spin up, spin down, spin up, spin down. Okay, this is called Pauli exclusion principle. First one. Okay, the second one is electron filling sequences and energy. Is that you need to fill in from the lowest energy to the highest energy. So you need to fill in electron from here, and next one is not if you have all electrons in a 3p, one extra electrons need to go to 4s instead of 3d, because we know that the electron fill orbitals from the lowest energy to the highest energy. Okay, the second rules. So the lowest energy to the higher energy is a function of occupancy. Okay, so you fill in here. If you still have space for the electron, you don't fill in this. You don't fill electron in this stage. So it's the occupancy. It's a function of occupancy. You fill in all the electron here before you go to 4s. So the energy level themselves change with the electron occupancy. Okay, and the differences between those energies level are becoming smaller and smaller. Energy level become smaller and smaller. The gap becomes smaller. This is bigger, right? It becomes smaller and smaller. Right. So filling energy state of electron here, that this is energy state, right? And then let's make an example, which is sodium. We have 11 electrons. Sodium atom has 11 electrons, so we fill in here first. So we call 1s2, 2s2, 2p6, and 3s1. So this is the energy fill up the lowest possible energy states in the electron shells and subshell. So 2 electrons per state, we call spin. So let's fill this first. 1 here. If this is spin up electron, spin down, right? This is what? Pauli exclusion principle, the first rule. And you go to the next one. The second rule is you fill in the energy state. You fill the electrons in the lowest energy state to the highest energy state, right? This is the one. You don't fill electron in this place, no, here, because you still have space in the 2s. Okay, and then what's the next? The next electron will fill in here, right? Because Pauli exclusion principle. Okay, so we already have 4 electrons out of 11. And the 5th electron will fill in here. Yeah. Okay, you might say, well, Professor, can I put the electron in this place? Of course, this is random. So, but what happened next? Will you put the electron in this place, using Pauli exclusion principle, or this one, or this energy state? Which one? This is what we call Hund's rule. Hund's rule tells us that if you have 3 energy state here, you want to have in orbitals equally energy drive the unpaired electrons. You need to put unpaired electron first. So the second one will be here. How about the third one? Third one is like this. This is called Hund's rule. You want to make unpair first, and then you make pair. Right? So next one will be what? This one, and this one, and this one. So how many electrons we have? We have 10. And then after that is the 11th electron. Okay, so now we already use 3 rules from the Pauli alpha principle. Okay, So this is the detail of the Hung's rule. As I just give you an example of 2p, right? 2p here. This is an example of explanation of Hung's rule. I don't want to tell you details, but what I want to tell you is that if you go to the bar, if you get on a bus and you sit here, somebody sit here, and then where will you sit? Will you sit next to him? No, you don't, right? You will sit somewhere which has more space. And this is pair. Right? If you regard two chairs as a same energy state, you will sit, somebody sit here, you will sit here. Okay? Unless he's a very handsome boy or very pretty girl, right? That's another story. But normally you will sit somewhere not too not too close to the guy. Okay, this is called Hung's rule. Easier for you to remember. Right. So so this is the principle. Instead of using this energy level diagram, we have another way to explain this. Let's make another example using carbon. The carbon has 6 electrons. And then this 1s2, 2s2, 2p2, right? So 1s1 is represent the principal quantum number. S represent the L, right? L equal to 0. And this one is the electron occupancy, number of the electron. And we use box notation instead of energy level diagram. Box notation is like this. So how many electrons? So this is 1s, and then 2s, and then 2p. 2p has 3 energy level, right? And we call it 2px, 2py, and 2pz. And then, okay, we have 6 electrons. Let's put the electrons into this box notation. First one here, right? First one, we put the lowest. And this is the quantum number. It can be spin up or can be spin down. For example, this electron is spin up. And this is the quantum number of this electron. And another one, where do you want to put the electron? Here or here? Here, right? Because we follow Pauli exclusion principle. So Pauli exclusion principle tells us that you have to put it here, and the quantum number will be what? If this spin up, this will be spin down, and follow the same quantum number. The first 3 quantum number first, 1s, and 0. So this is the quantum number of least electron. How about the second one, the third one? The third one is this, right? Fill in the lowest to the highest. Okay, so you put it like this. And then the fifth one is this one, 2px. And how about the number 6 electron? Number 6 electron, I'll put it here or here? Here, right? Because we follow Hung's rule. Hung's rule tells us that unpaired electrons. Okay, so this is the example of the carbon. And this can be the quantum number. This one, for example, if this, and then this is another quantum number. For example, it's all spin up. Although we don't know, but anyway, just make an example for you. Right. So just tell you this. This is the energy diagram for the multi-electrons. So this is 3D larger than 3D. The energy is larger than the 4s. And then there's 4D. 4D is larger than the 5s. So this is the exact energy state for you to know that. So 4s and 3D are very, very close, right? Okay, so what's the N error rules? So how do you know the energy of 4s is lower than 3D? We follow N error rules. It's like this. It's 1s, 2s, 2s, 3s, 3p, 4s. It's like this. If the energy level is packing like this. So this is called N error rules. What is N error rules? N is the first principal quantum number. L is second quantum number, right? If the N plus L is equal, that means we fill in order of the ascending values of N. You put the N first. For example, 3D is 5 because 3 plus D is 2, right? So it's 5. 4P is 4 plus 1 is 5. 5S is 5 plus 0 is 5. So what is this? Which energy is the lowest? We follow N error rules. So ladies and gentlemen, if if Friday I give you a Kahoot like this, you need to know I want you to rank the energy. Which one is lowest? You have to know what's the N here. Because 5S, see that? 5S, 4P, and then 3D. So 3D energy is lowest. So 3, 4, 5. 3, 4, 5. Okay? And another examples, 4D, 5P, and 6S. They'll have the same number of N plus L. And you pack the energy from lowest to the highest. Okay? But if you don't know, you can just use this as the example. Right. So this is our periodical table. The periodical table is also follow the NL rules, because you know that this is what? 1s. Hydrogen is 1s, right? Helium is what? 2s. 1s. So 1s1, 1s2, right? And this one is what? 2s. 2p. 3s. 3p. 4s. What's this? 3d, right? 3d. And then 4p. 5s. 4d. 5p. 6s. Next, not this one. 4f. And then go to this 5d. And then what? 6p. And next one 7, right? Okay. So you just follow any rules. You can make periodical table. Easy. Nice and easy, right? Okay. So these are all the four rules in the alpha principle. I hope you remember this. So it will be easier for you to know the electron configuration. You do it one by one, followed by this. And this is the energies. This is a little bit different from what you learned, but anyway, just for your information. Right. So the topic, the electron we talk in today and last week, we all regard electron as a particle. And now let's think of electron behavior like a wave. And in the end, we found out the equation we learned is the same if we use electron as a particle or electron as a wave. That's make the things wonderful. No matter how, you got the same answer. Okay, and today we are going to talk about wave mechanical model. Okay, now let's talk about wave mechanical model. There are three stories we want to talk in the wave mechanical model. The first one is deploying matter waves. You know, when we think of the light, the photon, we regard photon as a wave, but can matter as a wave. This is the first one. The second one is Heisenberg. We call uncertainty principle. The third one is Schrödinger. Schrödinger is a great man. I shouldn't say invent. He discovered the wave or he developed a wave mechanics model. Very good, wonderful. Okay, so let's think of the wave behaviors of electron. The wave behavior of electron is that De Broglie is saying that if a photon which has no mass, photon has no mass, it's very, very little, even no mass, can behave as a particle. When we think of particle, the particle always has a mass. What's the weight of the particle, right? And we found out by the photoelectrical effect, it can be a particle. Photon can be a particle. The experiment proved this, which is photoelectrical effect. Okay, he thinks photon can be a particle. Photon can be a wave and also can be a particle. Does it follow then an electron which has a mass can behave like a wave? So in the previous topic, we all talk about electrons as a particle. Can electron behave like a wave? So in 1924, the wave behavior of electron, you need to prove if electron is a wave, we need to prove it. The first one is De Broglie hypothesis. The De Broglie hypothesis thinks that, if electron is in the orbit and electron is a wave, so wave, there are two types of wave. The first one is called standing wave. The second one is destructive interference. That means it's not a standing wave. So which one you think it makes sense to you? Which one? If electron is a wave. So if electron is a wave, it has to be standing wave, right? Otherwise, the energy will lose if you have a destructive interference, if electron is not a standing wave. So it need to be like this. It need to be a standing wave, right? If it's not a standing wave, energy will lose. So a stationary orbit and geometry constraints, it need to be a standing wave. So electron behavior as a standing wave, they no longer emit energies in the form of a radiation. So it need to be like this. So if it need to be like this, the wavelength need to be times an integer number, like n times lambda, right? If this is not is the path is not n times lambda, you lose energy. So we call this circumference. C is m equal to m times lambda. And then m times wavelength, n equal to 1, 2, 3, 4. Okay? This is the first things you need to think. So circumference is what? If this is the one we know, and C equal to what? 2 pi r, right? R is radius. So you can put these two together. Am I right? I'm right, right? So these two are equal. So, okay. So the wave and particle behavior of the electron is like this. So 2 pi r equal to n lambda. And then you will know that the wavelength of electron is followed by this Planck constant divided by what? Momentum of the particle, which is the momentum of electrons. Momentum of electron is equal to what? M, mass times the velocity. So you can put this equation into this part, right? Okay, and if you rearrange this, it becomes like this. Is this equation familiar to you? Is this familiar to you? Yes, that's what we learned from last week. This is what? The postulation of the Bohr atomic model. Remember? So Bohr atomic model has a postulation which is angular momentum balance Bohr also give us this equation. So this is particle behavior, we have this equation. This is wave behavior, we have the same equation. Isn't it wonderful? Isn't it beautiful? Yes, right? Very beautiful. Are you excited to become a scientist? No? Okay. You want to be an engineer, right? To make money, not scientist. It's up to you. Okay, so if all the particle can behave like a wave, why we cannot see the wave? If the baseball player throw a ball, why we cannot see the wave? We can just see a particle. Why? Let's use this equation to do a simple calculation to realize what's going on. So assume the mass of a baseball is a 5 ounce, which is 0.142 kilogram. And the speed, the player can throw can be like 90 or 100 miles per hour, which is about, let's say, 94 meter per hour, which is 42 meter per second. Let's put the number into this equation. And then let's find out the wavelength of this ball. Can we? Or can we not? We can do it, right? Okay, let's do a simple calculation. I don't want to waste your time. I just do it for you. So the answer is the wavelength of this ball is 1.1 times 10 to minus 31 meter. Can you see this? Can you see the wavelength like this? Can you? No, you cannot. So it's too small to see. Too small to see. So once you are in your daily life, if the matter is huge or big, normally you can regard the things as a particle, not a wave. However, if we increase the speed, well, if the speed is very fast, okay, then the number will be what? The wavelength will be slow. The wavelength will be decreased again. Okay, according to this equation. However, let's take a look at the electron. Electron. Follow the same equation. Can we? Yes, we can, right? Okay, so if you do a simple calculation, we know that this is Planck constant. This is the mass of the electron. Okay, mass of electron you already know. This is 9.9 times 10 to minus 11, 31 kilograms. And what's the speed of the electron? Let's use the most simple case, which is the hydrogen. Okay, hydrogen model. The hydrogen model, the electron in the speed of electron in the N1, N equal to 1 will be what? 1% speed of the light. I hope you still remember. Let's put a number in here, in this equation. So what's the wavelength you can get? The wavelength you can get is 3.38 angstrom, which is 0.3 nanometer. Compared to this is much larger. The wavelength is much larger, right? So you can think of, yes, in this range, in a narrow scale range or in the atomic Armstrong scale range, you'll be able to see the behavioral wave of the electron in this range, in a very small scale. So even in a very small scale, you still cannot, because the wavelength is too small. But this one, detectable. Right? So how are we going to prove this, the wavelength? By interference. If you find out if you have an electron and which two electrons has interference, that means what? That means that electron has a behavior of a wave. So let's use a simple method to think. If you have a water, you have a barrier here, and this is lambda, right? The wavelength. This is the distance, the gap. If the d is much larger than lambda, assume there's no d here. The d is like this. There's no wave. You cannot see interference. However, you cannot. However, if d, lambda, and d is very, very close, you can see a diffraction. You can see a diffraction. That means what? That means this matter has a character of wave. Okay, if you see some kind of diffraction like this, interference. So this cannot be explained by particle-like behavior or particle-like properties. I think we run out of our time today, and we can talk about this on Friday. It's very interesting.